Have you ever wondered what the future of computing could look like? What if we told you biological elements might play a major role in it? Yes, you heard it right. We're standing at the dawn of a new era where the lines between technology and biology are blurring. Currently, our computing world is dominated by silicon-based devices. But imagine a future where our computers are built using molecules from biological tissues. This is not a concept from a science fiction novel, but a reality that scientists and researchers are working towards. This new frontier of technology is referred to as biological computing. Biological computing uses biologically derived molecules like DNA and proteins to perform computations. It's a revolutionary approach that could potentially change the face of computing as we know it. It's like turning the paradigm of computing on its head, where we don't just create machines that mimic biological processes, but use actual biological elements to compute. Intriguing, isn't it? Let's delve deeper into this fascinating world of biological computing. So, what exactly is biological computing, and how does it differ from the computing we're familiar with? This is a question that's been gaining traction in the tech world, and for good reason. Biological computing is a revolutionary concept that uses molecules derived from biological substances, such as DNA and proteins, to perform computations. Just as fascinating as it sounds, isn't it? Let's delve a bit deeper. Traditional computing, the kind we're familiar with, relies on silicon-based components to process data. These components are designed to follow a binary code, the ones and zeros, which form the basis of all computations. This system, while efficient, has its limitations, particularly when it comes to size and energy consumption. On the other hand, biological computing takes a completely different route. It steers away from the silicon-based components and binary code, and instead harnesses the computational capabilities of biological molecules. Yes, you heard it right. The very DNA and proteins that form the basis of life itself are utilized in this brand new approach to computing. Now, you may be wondering, how can biological molecules perform computations? That's where the beauty of biological computing lies. These molecules are naturally designed to interact with each other in precise ways, forming complex networks of interactions. These interactions can be mapped and manipulated to perform computations, much like how transistors in a silicon chip process data. So, instead of the binary codes, biological computing uses the 4 letters of the genetic code, represented by the nucleotides, adenine, thymine, guanine, and cytosine. Each interaction between these nucleotides can be used to represent a computational step. Essentially, biological computing turns the language of life into a language of computation. And it's not just about DNA. Proteins, with their vast array of shapes and functions, also hold immense potential for biological computing. These biomolecules can change their shapes in response to specific signals, and these shape changes can be used to represent computational operations. So, biological computing brings a whole new approach to the table. But how does it work? Let's dive into that in the next scene. Biocomputers come in different forms, each with its unique way of functioning. Let's get to know these fascinating machines a bit better, shall we? First off, we have biochemical computers. These clever devices utilize feedback loops in biological chemical reactions to perform computations. Imagine a maze where the correct path is determined by a series of chemical reactions. Each reaction leads to another, ultimately guiding us to the right exit. That's biochemical computing for you. Next, let's talk about biomechanical computers. These computers interpret the mechanical shape of molecules to generate an output signal. Picture a lock and key scenario. The key, or molecule, is shaped in such a way that it fits perfectly into the lock, triggering a mechanism that opens the door. In this case, the door could be a solution to a complex mathematical problem or a pathway to a new discovery. Last, but certainly not least, we have bioelectronic computers. These computers measure the electrical conductivity observed in the system as the output. Imagine a domino effect, but instead of toppling dominoes, we have a cascade of electrical signals. As each domino falls, or each signal is transmitted, it influences the next, creating a pattern of electricity that translates into meaningful data. Now, these examples are simplified for understanding. In reality, biochemical, biomechanical, and bioelectronic computers operate on a nanoscale, using intricate networks of biological agents, proteins, and DNA to perform computations. The molecules used in these biocomputers are derived from biological tissue, and the systems are engineered using advanced nanofabrication techniques. These are just the basics. The actual processes can be mind-bogglingly complex. But what does this mean for our future? Scene script. Biological computing isn't just a thought experiment. It has real-world applications and implications that could change our lives. Let's start with medicine. Imagine a world where we can detect diseases early, before they even show symptoms. The key to this could be biological computers. By using cells as their basic components, biocomputers could monitor our body's biochemical reactions, detect anomalies, and alert us to potential health issues. This could revolutionize early detection and treatment, potentially saving countless lives. But the applications of biological computing extend beyond medicine. Consider data storage. Our current storage methods have limitations, but DNA, a natural data storage system, can hold an enormous amount of information in a tiny space. By harnessing the power of biological computing, we could store the entire internet's worth of data in a space no larger than a shoebox. Then there's environmental monitoring. Biocomputers could be used to monitor environmental conditions, tracking changes in temperature, humidity, and chemical levels. This could provide us with valuable data, helping us to understand and combat climate change more effectively. But what does all this mean for society? The implications are vast. Biological computing could lead to breakthroughs in healthcare, technology, and environmental science. It could also raise new ethical questions about data privacy and the use of biological materials. Biological computing could fundamentally change how we interact with technology. Instead of rigid, mechanical devices, we could have flexible, organic systems that work in harmony with our bodies and the environment. This could lead to a more integrated, sustainable, and holistic approach to technology. Furthermore, biological computing could democratize access to technology. With the ability to create biocomputers using common biological materials, technology could become more affordable and accessible, breaking down barriers and driving innovation. As we can see, the potential of biological computing is vast, but how far have we come in realizing this potential? How far are we in the journey towards fully functional biocomputers? And what does the future hold? Well, the path to fully functional biocomputers is an ongoing journey. Currently, we are in the exploratory phase, where researchers and scientists are harnessing the potential of biologically derived molecules like DNA and proteins to perform computations. From biochemical to biomechanical and bioelectronic, different types of biocomputers are being developed, each with its unique approach and potential. In terms of breakthroughs, we've seen significant strides in nanobiotechnology. This field, which combines nanoscale materials with biologically based substances, has opened the door to the creation of functional biocomputers. It's like building a computer from the ground up, but instead of silicon and metal, we're using proteins and DNA. However, it's not all smooth sailing. Challenges abound, particularly in the synthesis of the necessary chemical components and the engineering of cells to act as basic components in biocomputers. But with every challenge comes an opportunity, and these hurdles are just stepping stones on the path to progress. So what does the future hold for biological computing? Well, it's bright to say the least. We can expect to see more breakthroughs in the coming years as research deepens and technology advances. Scientists predict that we might see fully functional biocomputers within the next 2 to 3 decades. This is not just a wild guess, but a calculated projection based on the current pace of advancements in the field. What's even more exciting is the potential applications of these biocomputers. From medical diagnostics to environmental monitoring, the possibilities are endless. Imagine a world where computers can diagnose diseases or monitor environmental changes at a molecular level. That's the power of biological computing. In the end, it all boils down to this. We're on the brink of a revolution in computing, and biological elements are at the forefront of it. The journey might be long and fraught with challenges, but the destination is well worth it. The future of computing is exciting, and biological elements are set to play a starring role in it. Let's take a moment to reflect on what we've learned about biological computing. We've delved into the fascinating world where biology and technology collide, exploring the concept of biological computing, where biologically derived molecules such as DNA and proteins are used to perform computations. We've discovered the 3 distinct types of biocomputers. Firstly, biochemical computers that employ feedback loops in biological chemical reactions for computational functionality. Secondly, biomechanical computers that interpret the mechanical shape of molecules as the output signal. And lastly, bioelectronic computers that measure the system's electrical conductivity as the output. We've also touched on the potential applications and implications of this groundbreaking technology. The possibilities are immense, from solving complex mathematical problems to revolutionizing medical diagnostics and treatments. Finally, we've peered into the future, examining the current progress and future prospects of biological computing. With the aid of nanobiotechnology, we're synthesizing the required chemical components, including proteins and DNA, to create functional biocomputers. As we stand on the cusp of a new era in computing, one thing is clear: the future is biological.